Society's need for infrastructure has grown astronomically, and robotics can fill that need. So, what we're going to be doing is taking concepts learned in robotic manipulation and emulating a large-scale construction task, such as what we have right here before us. We will be creating a hydroelastic model of these large Lego-like bricks and getting a robotic manipulator to perform a pick, lift, mate task, just like you would see in construction.
Rather than small Lego bricks, we picked these larger Bigo bricks to more closely model things that might be used in construction. We create a hydroelastic simulation, so we need to figure out each part. The key difference between these and Lego bricks is the stud shape. Lego bricks have circle studs which can be modeled as cylinders, but here with this rounded cross shape, we need to create custom files in tri-mesh. However, even with these differences, the behavior remains the same. The studs squeeze the tubes and create friction. So to model this, we make the studs to be rigid and everything else to be hydroelastic. Once we have these, we had to tune them in order to get the right behavior by setting the mesh resolution and size of the cylinder and also the push force of the robot. We set up a bridge between Drake and the UR5E using the robot's real-time data exchange interface. This bridge translates joint commands published from Drake into RTDE motion commands. It also streams the robot's measured joint positions, velocities, and torques back to Drake in real time. In principle, we can use this to implement closed-loop control of the robot in Drake. However, we found that due to processing times and communication latency, it was better to first compute the desired position trajectory in Drake, and then send the joint commands to the robot. We make use of the RTDE measurements to collect data for our experiments.
To obtain a stable grasp, we 3D printed TPU fingertips for our gripper. TPU is a rubber-like filament with high mechanical compliance. We designed these to fit the concave regions between the studs on the top of the bricks, so that we have an antipodal grasp that provides stability against disturbances. We designed our system so that we can place the bricks wherever we like on the table, and the robot will be able to find them. Using a calibrated depth camera, we obtained the RGB-D values for each pixel in our scene. To isolate individual bricks, we run segment anything to generate a set of object masks. We then use grounding dyno, an open vocabulary detector, to filter these using natural language prompts, such as green brick on the right. Once we have the masks, we back project the depth pixels into 3D points and transform them into the world frame. Using iterative closest point, we align our model bricks with the point cloud. We use soft correspondences so that our alignment is robust to noise. Once we've done this, we know where to grasp the brick and where we would like it to go. Using Drake's inverse kinematics solver, we compute the necessary joint configurations for the UR5E. We then plan a path in Drake and send it to the robot.
For our experimentation, we are interested in testing both the robustness of our integrated system as well as learning more about the trade-offs of different RRT implementations within Drake. We looked at 5 different RRT algorithms: RRT, RRT with shortcutting, RRT star with 3 different iteration counts. For RRT without shortcutting, we found 2 results to note. For starters, the path chose a non-trivial path to reach the goal position, which is to be expected. However, we also saw that the path was divided into 70 waypoints for the non-trivial path, leading to intermittent pauses in the robot execution. For RRT with shortcutting, a straightforward path was found with fewer waypoints, but at the expense of higher computation time. During the RRT star trials, we found that trials with higher iteration counts yielded significantly higher computation times, but generated direct and energy-efficient paths. However, as the iteration count increased further, there were diminishing returns, in which run times remained relatively constant while computation times continued to increase dramatically.
One of our limitations was reliably getting the bricks to mate in Drake. At first, just using position control, we could only mate the bricks when our pre-push was extremely accurate. The real bricks were much more compliant. In order to overcome this, we developed a stiffness controller for the UR5E and Drake, which led to much better results from pre-push to push. Future work on this project involves getting stiffness controller to work with the real robot and trying other motion planning algorithms such as GCS.